Good afternoon, ladies and gentlemen. My name is Kateřina Slaninova. I am a senior researcher from IT for Innovations National Supercomputing Center in Czech Republic. And it is my pleasure to welcome you today at our next IOC training event. Today it will be hands-on training with data access and storage interface called DASI. This training event will be led by 3 tutors, Metin Çakırçalı, Jenny Wang, and James Hawkes from ECMWF. The training itself will be organized as following. We will start with introduction to DASI. Then you will hear about how to use DASI, and you will hear also the use case example. After that, we will have a short coffee break, and then we will follow with 2 hands-on sessions. The first one will be focused on archiving data, and after another coffee break, the second one will be focused on retrieving data. And we will end with Q&A and wrap up. But first, let me briefly introduce our IOC project for the newcomers. So the IOC project is focused on storage I/O and data management for exascale architectures. The project itself is part of the C project family, which all addressing modular supercomputing architectures. This project family is funded by the EuroHPCJU and the call, which is focused on software and applications. And the target of EuroHPCJU is to build exascale computers in Europe in 2023-2024. The project family consists of 3 projects: DeepC, IOC, and RedC. DeepC project is focused on software for exascale architectures. RedC is focused more on network solutions, and IOC project on input-output software and hierarchical storage. The consortium of the IOC project consists of 11 partners. The leader, the coordinator of the project is CEA. And this training will be led by tutors from ECMWF. And here you can see overall scheme which focuses on the goals of the project itself. As you can see, the project focuses on design and development of management and storage platform, which is based on hierarchical storage management, usage of object stores, on-demand ephemeral provisioning of software services and scheduling, and also, which is on the top of the scheme, the co-design with the next generation IO-intensive HPC-oriented applications. And here we can see that we have new flexible application interface called DASI, and this will be, today we will focus on this topic. The training today will be led by 3 tutors. Metin Çakırçalı, who is a software developer at the European Center for Medium Range Weather Forecasts, ECMWF. He has experience in the development of 3D visualization tools, graphical user interface, and numerical solvers in high-performance computing. The second one is Jenny Wang, who is a research software engineer in the data processing services team at ECMWF, primarily focusing on the development of a new framework for the statistical processing of ensemble model outputs. Her academic background is in theoretical physics, and she previously worked in the Space, Weather and Atmosphere Group at the British Antarctic Survey. And the third one is Dr. James Hawkes, who is a team leader at the at ECMWF, and he is specializing in meteorological big data software development. His background is in engineering and high-performance computing. He has researched numerical method scalability intensively, and he holds a PhD in chaotic multigrid solvers. So this is briefly from me. And now I would like to give the floor to our tutors.
Thank you very much, and Karina, and thank you for hosting this training event, the DASI. So Katerina's already given you an overview of what we're going to do, just to build on that slightly. So in the introduction session, we've got 2 short presentations. The first one by myself, giving a bit of background about ECMWF and the importance of semantic data management, to try and give you some idea of where we come from with all of this, why we're doing all of this. And we're self-declared experts in semantic data management, and I hope to give you a sort of glimpse as to why that's the case. Then there'll be a presentation from Jenny, talking more about our particular involvement in the IOSEA project, and also on the DASI, which you'll be getting hands-on with in the later sessions after the coffee, in some Jupyter notebook sessions that Metin has organized. So without further ado, let me jump into my first presentation. So we are ECMWF, that's the European Centre for Medium Range Weather Forecasts. We were established, don't want autoplay on. We were established in 1975. We're an intergovernmental organization, which means that we are paid for by a combination of governments from all around Europe. I think it's just this slide that likes to go ahead. I think you'll get over it. We currently have 23 member states and 12 cooperating states, and 350 staff in 3 centres around Europe. We have our headquarters in Reading in the UK. Our data centre is in Bologna in Italy. And we also have a second office in Bonn in Germany. We're a 24/7 operational service that runs global weather forecasts. So our remit is global medium range, which means up to about 15-day forecasts. These global models feed into member states models around Europe. So the UK Met Office, the German DWD, for example, they all use our global forecasts, usually as seeds, boundary conditions for their regional forecasts. We're also a research institution, so we're continuously doing R&D to improve our models and to improve our analysis. And we also do a lot of climate research with climate reforecasting and climate reanalysis. You may be familiar with the ERA 5 datasets, for example, which are long-running climate reanalysis datasets used for climate research. We also operate 2 of the EU Copernicus services, the Climate Change Service and the Atmospheric Monitoring Service. And we also support the Emergency Management Service with flood and fire forecasting. We're also one of the major 3 partners in Destination Earth, where we operate 2 of the digital twins, the Weather Extremes digital twin and the Climate digital twin. So I want to step into what our production workflow looks like in ECMWF, because this really sets the scene for why we've had to pay. Okay, it's doing all my slides. Just give me a moment. We're not used to sharing with Zoom. We're all in the Teams ecosystem now. Let's try again. Okay, so our operational workflow really sets the scene for why we have to be so careful with our data management. And this is what it looks like for us to produce a forecast from end to end. So first of all, we're receiving global observations from all sorts of sources around the world: satellites, weather stations, weather buoys, sensors on aircraft. In total, we receive about 200 million observations per day, which feed into our acquisition system. These observations feed into our Earth system model, which is where the main forecast runs. We run one deterministic forecast at a high resolution, and we also run a 51-member ensemble forecast. Each time this Earth system model runs, in each cycle, as we call it, we produce about 30 terabytes of data in 1 hour, totaling 120 terabytes per day because we run 4 cycles per day. The raw output from our model is fed straight into the product generation system, and this is where we take the raw data and post-process it for particular clients, particular member states' needs. So this might be regridding to different grids, cropping out certain areas. For example, Germany might want to boundary conditions from Germany. This is where we would crop that region out to filter the data for them. About 45 terabytes of products are produced every day, and these go into our product dissemination system, which sends data out over the internet to our member states and our commercial customers. In parallel to this, and slightly offline, we also write everything, all our observations and all our raw model output to our perpetual tape archive called MARS. But the interesting thing about weather data is that it's incredibly valuable, but not for very long. If it takes you 6 hours to deliver a forecast, then it's too late because that data is already old. So everything from when we cut off our observation window to delivering the data to our member states basically is in our time critical path, where we have about 1 hour to run everything. So our Earth system model running on the HPC using thousands of nodes, product feeding straight into product generation, product dissemination, all of this has to run in a very time critical manner. And in this time critical window, there's a lot of I/O happening. So the Earth system model is writing 30 terabytes to the parallel file system on our HPC. We're immediately reading about 70% of that back into our product generation system, producing products from that, which go back to the parallel file system, and then product dissemination is reading from that and sending it all out to our member states. The theme you start to see here is that basically everything is coupled via the I/O, via the parallel file system. So another way of drawing our workflow is to look at it from the data point of view, in which case everything is basically coupled. And this parallel file system is central to everything we do. We have the Earth system model reading and writing from it, product generation, reading and writing from it, acquisition, sending, putting observations in, product dissemination, pulling raw data out, products out, and also reading from this system to store in our archive. Now, because we have so much data flowing around in all sorts of different ways, labeling and indexing and organizing our data is absolutely essential. And so what we do is something called semantic data management. And this is a method by which you index your data using scientifically meaningful keys. So semantics means words that carry meaning, basically, or the meaning behind words. In our case, we're talking about indexes that have meaning. So in the bottom right there, you see an example of a semantic key, which is basically a dictionary of key value pairs of scientific information. So this semantic key down here tells us what date the forecast was run on, what cycle it was. This was the 12 o'clock cycle. Step 24 refers to data output from the forecasts for tomorrow, 24 hours in advance. The parameter is temperature, and level 0, which is the upper atmosphere. And that that key is used to uniquely identify the data. And if you're used to dealing with S3 object stores and other things, you might have UUIDs to access your data, to identify your data. Or you might store your data in a file path, for example. In both cases, those indexes don't really carry any scientific meaning. And to be clear, this is going a bit of a step further than just storing metadata with the data. You should always store your metadata with the data so that when you do find your data, you know what it is. We go a step further and we use this index to uniquely identify the data and use it to access the data. So our tape archive called MARS, currently it's the largest meteorological archive in the world, stores over 400 petabytes of data, and every single byte of it is addressed using a language, a hierarchical schema which describes our data. So you can find any data in MARS using a semantic scientific key. Now, you've probably done some kind of semantic data access. If you've done a big research project, or you've just organized your holiday photos, for example, you may have put them in a file structure where you've said, okay, this was my holiday to Greece, this was my holiday to Italy, maybe you put the date there or something, and you have a file, you have a POSIX structure which gives you some explanation about what your data is and where it's stored. But a proper implementation of this needs to decouple the scientific identification from the storage resource. Because the way we want to lay things out as humans, which might be by location we took our holiday and the date we took our holiday, is not necessarily the most efficient way of storing data on that resource for example, an HPC model with 1,000 nodes to write to. It may prefer to write, per per MPI rank to a different folder, for example. So what we do is we build an API where everything on the user side, the science side of the API just has to deal with a nice semantic description of their data. And behind the API, we can hide exactly how the objects are stored. And we're not tied to a single storage resource either. We can store in POSIX, we can store in S3 buckets, we can store in memory locations or tapes. And there may not be a one-to-one mapping between the scientific objects and the objects on the storage system. So for example, if your objects are really small, we might want to pack 10 of those objects into a single POSIX file, because maybe that's more efficient in that particular case. But the important thing about this API really is that it abstracts the users from having to worry about the storage. And when we're building fairly complex I/O systems, as we do in IOSEA, for example, this becomes even more important, because you don't want to expose scientific application writers to the complexities of dealing with NVRAM and stuff like this. It's not an efficient way of working. So going back to our diagram where we have everything coupled by the parallel file system, well, for most of the people writing applications, for the people who write the Earth system model and the product generation, they never see the parallel file system. It's a black box to them. We have an API, which is the dotted line around this black box, which is what they interact with. And inside this black box, we can do anything we want. So we might replace the parallel file system with NVRAM or Intel DAOS, or maybe we make a tiered system where there's a parallel file system with a faster performance layer inside it as well. None of the applications need to change for us to be able to explore these technologies and develop new solutions. And this is vitally important to us as a center, because it means we can develop cutting edge I/O systems without having to mess with the scientific side of the applications, so that we can develop in parallel really well. This semantic indexing is not just used for storage, though. It's also a language that we use to describe data routing through the center as well. So we're looking now at some technology for on-the-fly post-processing, which is also part of the IOSEA project in some ways, in which the Earth system model says, okay, I'm writing a temperature field. But we may decide on the back end that actually it's more efficient to stream that temperature field directly to product generation and never go to the parallel file system, because maybe we know the product generation has already started and we can send it directly. And so we can intercept here and do intelligent data routing through the center, and we can redirect, for example, operations onto different file systems or through different processing routes and so on. So we have quite a large I/O software stack, which is all built around this semantic data indexing. In the first instance, we have the data storage, which is a piece of software called the FDB. And as you'll see later, the DASI is directly built on top of FDB. FDB is domain specific. DASI is designed to be not domain specific, so that we can use it in other scientific domains, not just metrology. And hopefully that will be applicable to some of you today. We also have software for doing data aggregation on the fly post-processing. We have externally facing APIs for data extraction and data notification. And we also have our tape archive with its own API. All of the interfaces to these components are all based on semantic data indexing. And I'm going to go through these components, just a slide on each, just to kind of give you an idea of how these different systems work with this kind of semantic data indexing. So the FDB is the first one, and this is kind of the root. It is that black dotted abstraction around the parallel file system that I talked about. It's our object storage. So it's a key value store where the keys are the scientific metadata, and the values can be anything: byte streams, binary objects, whatever you like. We already have support for multiple backends here. The POSIX file system is the one we use for our operations. We also have an Intel DAOS backend, a Ceph Rados backend, and a Motor Cortex backend that we've developed in IOSEA. So the FTB is the software that makes the decisions about how to take your scientific objects and map them efficiently to the hardware. And in most instances, the layout on the hardware will look nothing like the kind of scientific view of how the data should be organized that people are used to. So it does a really valuable sort of translation here that makes sure we can store these objects very efficiently. The API, as you'll see later, is very similar to the DASI API, where we can put data objects in, describe them with their semantic index, and we can retrieve data out using a query. So this query down the bottom here, we're saying we want to retrieve all the steps of a particular forecast for all the available vertical levels of the atmosphere. And then to show how this can be used for data routing, our multi-IO software is our multiplexing IO server. It does aggregation of the massively parallel HPC job onto IO servers, where the fields are aggregated into global fields. And then in between that aggregation and when we write the data out to the FTB, we have the opportunity to do some on-the-fly post-processing. And we describe the different pipelines of processing that we want to do using our semantic metadata. So for example, just to look at the bottom example here, if the type is wave, so if that's in the scientific keys, maybe we're going to reinterpolate all the wave data to a different kind of grid, like a regular lat long grid, for example. And then we encode this in a particular way and write it to the FTB. So we can do kind of this on-the-fly data routing using the semantic metadata to describe it, which would be quite hard to do without semantic metadata. You'd need to come up with some other way of labeling data kind of in memory inside your MPI job and building a sort of configurable structure that can do this. But by using the semantic metadata right from the start, from the point where the air system model is talking to the IO servers, we can simplify this process a lot better and make these systems more interoperable. Our externally facing APIs also use the same kind of semantic data access. So we have an API for extracting data from our data cubes of metrological data. So the hierarchical schema that defines the keys in our data sets can also be thought of as an n-dimensional data cube. So for every date that we run the forecast, for all the steps available, all the parameters, each of these is basically another axis of the data cube. But we have something like a 7 or 8 dimensional data cube if you include all the metadata keys that we set. So we've built an API that allows extractions from these data cubes. So you can extract flight paths crossing 3 spatial dimensions and the time dimension, for example. You can cut out polygon regions and so on. The requests for these shapes are all defined using the semantic data language. So you ask for a lat long region or a time series by specifying a range of steps, for example. And the users that interact with our data are only seeing those keys. If you go to the government website to download, I don't know, geographical information of urban planning or something, you're probably going to get sent to an FTP server or something like this, and it's up to you to kind of figure out their folder structure and find out what the data is. And if you're lucky, they have some kind of README that tells you how. But using the semantic data languages, it's almost self-describing. If the user knows roughly what your schema looks like, what the metadata keys are, it's very easy for them to figure out, okay, if I want to get pressure data, I probably have to set parameter equals pressure. It's a bit easier to use in that sense. Parallel to this, we also have a notification system for data availability called Aviso. So this is designed to couple workflows. So for example, the Swiss Meteo service, Meteo Swiss, they might want to run their regional model after our climate model has finished, and they want to be notified when it's finished so they can start their workflow. So they use Aviso for this. And basically their query for Aviso is the same set of semantic metadata keys. So in this case, they're asking when any cycle, any step is finished, and there's a parameter field available, I want to be notified because I'm going to do something. Maybe I'm going to update my website by downloading the data and producing a plot. So these semantic keys are not just used for data access, but they're also used for data management and workflow management as well. And finally, probably where the need for semantic data access really started is our metrological archive. So we currently have 400 petabytes of metrological data stored on tapes. adding about 150 terabytes per day. We have 5,000 daily active users, over 2 million requests per day. And this storage system has been running since 1985, storing every single forecast output and all the observations that we've received in that time. It's an incredibly valuable resource for research and for climate research, and also for going back in history and looking at the state of the atmosphere over the decades by replaying old observations and things like this. From the very start, we've needed a comprehensive way of being able to index and store data in this tape archive. So this is when we started doing semantic data indexing, and the schema that we defined for meteorology is what we call the Mars language. And this is now what we've adopted through the whole center and our entire software stack for describing data. So if you include most of the keys in a Mars request, this is kind of what it looks like. That's sort of the full schema that we have. It varies depending on which sort of type of data you're looking at, but pretty much every single byte in the Mars archive is addressable using a metadata index like this. So I'm going to hand you over to Jenny in a minute, who's going to talk a bit more about the IOSEA project and DASI in particular. But hopefully this has given you some background into why we're so keen on this kind of semantic data indexing. I'm happy to take any questions now, if anyone has any. Then I will hand over to Jenny, who's going to talk about IOSEA and DASI.
I will, just before we go through to the hands-on part of this event, I'll just give a short presentation on how DASI kind of fits into the IOSEA project, the concept and design of DASI, and then briefly introduce the Python API that we'll be using in the hands-on part of this later on when Metin takes over. So, okay, so as Katerina already mentioned, the IOSEA project kind of focuses on novel storage and data access architectures for scaling IO-intensive applications to the X-scale HPC systems. So as she's already kind of brought up this diagram, I'll just briefly mention that, so DASI really, which is shown in this diagram kind of here, is really the layer that sits between user applications and the hierarchical storage management, which is kind of this chunk down here. And it's an application interface, as James already mentioned, for managing and accessing data, but also to abstract complex storage layer from the users. What is the design and the concept of DASI? So the concept of DASI, as mentioned by James, is to provide a scientifically meaningful way to manage data, then can be in a way that can be configured for use in any scientific domain. And it also abstracts the underlying backend storage so that the management and usage of data is kind of decoupled from how it's stored. So, for example, often data is kind of labeled by a unique identifier, but it doesn't provide any description of its contents, or it's described in a way that is tied to how it's the underlying storage implementation. So the idea of DASI is really to couple this knowledge of the backend storage system and also provide like a scientifically meaningful way to access and manage the data. So this is, as James already kind of discussed, the data is addressed by key value pairs. So here on the left-hand side, you have a set of keys that's configured by the user. And then a particular piece of data stored in DASI will require specification of values for each of these keys, so that as a way of uniquely identifying it. Okay, so the application programming interface of DASI kind of consists of data management and access commands such as archive, list, and retrieve, which are operated using the metadata keys configured by the user. The DASI core is responsible for validating these keys and queries according to the schema, and also converts keys and queries into a set of normalized terms. So it kind of, if you have like a query that involves ranges over dates or other metadata keys or wildcards, it'll expand all of these out before trying to find the data matching these particular key values. And then there's two layers of abstraction. So the DASI index is really responsible for resolving object locations from the metadata keys. And it's also responsible for creating and deleting entries in the index. And so when you kind of query the data archived in DASI, it's this index backend that will return the list of metadata keys that match the query. And then the data store backend is responsible for implementing atomic operations, such as put, get, delete, for interacting with the backend storage technology. So here on this diagram on the right-hand side, you can see that DASI here, which has various application programming interfaces, is really built on top of the FDB, which James mentioned earlier. And this allows it to be able to make use of the different backends that the FDB has been adapted to use. So in the simplest case, you have a POSIX backend, where the DASI objects are just stored as files. But then there are also, more other supported backends include the self object store and then also MVRAM. But all of this is kind of hidden away in the application programming interface of DASI, so that user applications don't need to know about how to interact with these backend storage solutions. Okay, so now we'll, just as a preparation for the hands-on part later on, we'll just talk a little bit about the DASI API and how you use it. So as shown in the diagram before, the API, with various APIs, but we'll mainly be focusing on the Python API in this hands-on demonstration, but there's also a C++ and a command line interface to DASI. And DASI is configured through defining a set of rules. So you need to first identify kind of your semantic metadata keys that are associated with your data. And so in this example here, we have keys of kind of user, project, date, and time, and processing. And then you need to determine a hierarchy of 3 levels for these metadata keys in the definition of your schema. So here we've assigned the top level to user and project, and then the other 2 levels kind of nested inside these brackets for the second and third levels. So you can, and this defines one rule in the schema. So the schema in this case just consists of a single rule, but actually in more complicated cases, you can have multiple different rules which consist of different metadata keys, and each of them kind of having the structure of having 3 levels. And data is accessed by DASI by providing all keys from the root to the leaf of this kind of tree. So for example, you would need, in this particular case, you would need to provide all 5 of these values for each of these keys in order to access a piece of data, like a unique piece of data in DASI. So here, this is an example address for some data where I've put just an example values for each of these keys. Main burden on the user of using DASI is to devise a suitable schema for their use case. So when building a schema, the user needs to first identify the data collection that they want to be working with, and also then what are the data objects in this collection. So for example, here we'll use one of the IOSEA use cases, which is cryo-electron microscopy, where they kind of store images, like microscopy images. Okay, so then you need to define what your metadata keys are for uniquely identifying objects. As we kind of briefly touched on in the previous slide, the schema allows multiple rules consisting of different sets of metadata keys. So it's important to know which keys can be used together for addressing objects uniquely. So in this simple example, we just have a single set of keys, 6 keys, when we're not dealing with different subsets just yet. So given these 6 keys, we then need to determine a hierarchy. between these metadata keys, splitting them into 3 different levels of hierarchy. And this isn't, as we'll show this in the next example, the schema does support branching. But in this particular example, we don't have any branching, so we assign 2 metadata keys to each level. And all of these need to be specified when trying to retrieve a unique piece of data from DASI. So now if we look at a slightly more complex schema, where we have more than a single rule, and we can see that in this first one, this is very similar to the previous schema where we have those same 6 metadata keys, but here we have an example of branching. So here on the 3rd level, we can either provide a value for the processing metadata key or the type. So it means that a unique address for a piece of data would consist of 5 values for either these top 4 with the processing or the top 4 with a value for type. And in the case of a POSIX file system backend, we can think of the different levels of hierarchy in this way. So the top level specifies the top level directory. The 2nd level specifies a file name inside this directory, and then the 3rd level indexes entries in the file. So we'll see this later in the demonstration today. If you look inside, because we'll be working with the files, you'll see inside the DASI store that actually this is how the data is organized. That we probably won't be touching on these kind of complex aspects of the setting up the schema today, but there's also possibility of putting in optional metadata keys here, which is represented by having this question mark here next to location. Cool. Okay, so then the final slide was really just about how the Python API for that we'll be working with today. So so the creation of a DASI object requires a configuration file, which specifies the location of the schema file that contains these different rules and the metadata keys. So that's in this kind of top line where we create the DASI object. And then to archive data into DASI, we must first specify a set of this keys and values, which in the form of a Python dictionary, which is compatible with one of the rules in the schema. And then you pass this key along with the data in the form of a byte stream to dasi.archive. And to retrieve the data that has just been archived, we call retrieve on the DASI object with this query that has the kind of same set of metadata keys and values that we just used to archive it. There's a slight difference in the syntax between archive and retrieve, and this is just because when retrieving, you can actually put multiple values for each key in order to kind of retrieve multiple data entries at once. So they're not just a single value inside. Yeah. And this will return you all the data that matches the specified kind of values in this first part of the key as a byte stream. And then you can also use DASI to query the data inside, which doesn't return you the data itself, but it just returns you kind of all the metadata of the data that DASI contains that matches on your query. So we may or may not have touch on DASI list, but we'll definitely cover the archive and retrieve in the hands-on part today. Cool. And then the final part, I just wanted to mention about the different use cases in the so at the end, just wanted to mention that there's the applications and workflows which in the IOSEA project, which really span a wide range of different domains that have been adapted to use DASI. So you've kind of heard from James how we use this semantic data management and access extensively across ECMWF. But there are also use cases in IOC such that are in lattice QCD, astrophysics, terrestrial systems modeling, and electron microscopy, and which all differ in their scientific domain. but also the type of data that they work with. But they've all been adapted to, use DASI. Okay, that's the end. Thanks.
So the hands-on session will be led by Metin. Metin is the main developer of DASI. Over to you, Metin.
Thank you, James. So I think the first thing to introduce the Jupyter Hub that we prepared. So we prepared for DASI Python API. We prepared Jupyter Hub and a couple of training material. So maybe the first thing is to talk about an important thing that we noticed. There's a technical issue with the using notebooks, which is not an issue when you use a Python file, and that is when you run the cells in the notebook, the first run always somehow results in 0 bytes files. So to work around that, we need to run the cell twice, but I will show it, or I will demonstrate it, what that actually is. That issue actually is later on. So when you log in, you will see that there are a couple of directories. One is data, and this data is the directory that we prepared for you to use during the training session. And inside there will be a list of grip files. These are the simulation output, so to say. These are the raw data, original data that we are going to save or archive in DASI data store. And there's another directory called demo, and this is a very simple usage of archive and retrieve in Python. I will go through this demo directory and talk about very basic usage of retrieve and archive. And then we have also the main directory that we will be using is the hands-on. And this is a simple weather forecast there, data archival, retrieval, and plots of the data that we retrieved. So there are 3 main directories in the for each account. So in the demo, I will jump into this demo case. It's a simple archive example. So we will not focus on the configuration file of DASI, but I will talk about it. So inside the configuration file, this is a YAML format file where inside we define where to find the schema file. In this case, it's called schema. And we define also some of the options for the indexing and storage of the data files, which are not relevant for this training. And there are also other options such as spaces, and the spaces is that we can define multiple folders or directories to be used later on, which has individual characteristics such as one folder or one root may be that you are not allowing it to wipe any data from it, or you may say, okay, you can archive, but we cannot retrieve, and so on. So the important part of the DASI archival and retrieval or DASI usage is the schema file. Inside the schema file, as Jenny explained, we have set of rules. In this case, there's just one example rule, and it has 3 levels. So first level is user ID, institute, and project. And the second level is type and date. And the third level is experiment and name. So what's the difference, or what's that supposed to mean is when we look at the root folder, in this case, we used user ID, institute, and project. And later on, we define what this user ID is, what the institute is, and what the project is. And this then becomes the first level where when we say save it inside, archive it inside the root, then this becomes the name of the directory, master forecast IOSEA. And if we look inside, then we see that the second level information is then the type and the experiment. In this case, we set it training, and type is training, and the date is 5th of December 23. So the other thing to notice is that whenever we archive in DASI, we do not overwrite the previous data. So we would, if we run the archive again and again, then we would populate here with the multiple set of files, data and index. So as you can see here, the first time I ran this notebook cell to archive, it ended up with 0-byte file, but actually that's not a problem if we used a Python file. It's just something that we need to be aware of, and that we run it twice so that we work around this problem just specific to this notebook. So coming back to schema, so we need to look at our data, what the data means, what the metadata is about, and we need to come up with a rule in a and put it in a schema file. So that is the first starting point. And and when we store the data, then we need to provide this metadata defined as a rule in the schema file. And here's user ID is master, and institute is forecast, project is IOC, type is training, experiment is called semantic, and name is demo, and date is also defined, given. And then the next thing is, of course, we need the data. In this case, it's just a simple data. It is a string. It says DASI training data with key, blah, blah. And then if you look at it, how to archive this data is very, very simple. We need to create the DASI object showing where to find the config YAML file. And then we need the key, which we defined here. And then we need the data. And then afterwards, we need to archive it. So I already did this before this training course, and this would basically be the archival. And after that, of course, DASI will create this database, and we now have all those data that we stored, archived before. And now to retrieve a very simple example, to get data from DASI database. So for that, we again need to look at the schema, and in this case, in this example, it's user ID, institute, project type, date, experiment, and name. So we need to provide what we want to retrieve from the DASI data store. And for this is the query, and there is a small difference between key and query. And in Python, we need to provide these curly brackets, because if you look at date, for example, you may want to retrieve multiple dates, which is the case in this example. So when we look at the schema file, what it is, and we need to create the query to retrieve the data from the DASI store database. And for that, it's also similar to archive. We need to create the DASI object telling where to find the config file, and then we need to call DASI retrieve and pass the query that we created. And in this case, we may retrieve multiple data. So as I mentioned, if we set multiple values for a query key, then we would fetch multiple, we would retrieve multiple data. So that means that what we return from retrieve is it's an iterator, and we need to iterate, loop over this object that is returned by the retrieve. And in this example, it's very simple. We retrieve the data from DASI store, and then we loop over the retrieved items. And we can then, what is important to know is that we retrieve each items would have keys and the data associated with this item. So that is the important or critical point that you need to know before the hands-on. So when we retrieve a key and data together as an item from the DASI store. And you should have access to the to this demo on your Jupyter account, and you can anytime look at there and use it as an example for the hands-on. So for the hands-on part, you should have a hands-on folder, and inside you should have task 1, archive weather forecast data in DASI store. And so the task 1, archival of weather forecast data into DASI store, is about a situation where we have data, original data that we want to archive in DASI, which is here represented by this temperature 2023 11/25, which is the date, and 18 is the time for this data. So we will extract this metadata from individual files. We will read them and we will archive these data into DASI. So our goal is to first think about what we need to put into the schema file as a rule. And with that, we need to think about the metadata, which is for example, here, temperature, there's date, and there's time. And we need to complete this this schema file and move on to the next step. So the first step is to looking at the data. What is the original raw data, and what would be the metadata for this case, so that we can come up with a meaningful, scientifically meaningful semantic description that would fit as a rule, and put this rule in the schema file. So if you maybe we can say for 5 minutes we can work on this, and after 5 minutes we can think about, we can ask for feedback, how it is going. If there is any questions, please feel free to ask anytime and give feedback how it is going. So what we are supposed to do is, again, to think about the schema file, what the rule should be. So we have original data called temperature or rainfall, and a couple of different dates and time. So to me, I think one example was that what I came up with is, okay, I can say institute ECMWF. And I also thought, okay, this data maybe is coming from a channel, and I called it global. Maybe there's also local, what local actually is, like Europe. It could be Europe. So I came up with this institute and channel as an example, but I left, there's A, B, and C. So there's second level and third level. So for the second level, of course, one could think of it like, okay, there's temperature, rainfall. This, if I think about the metadata, maybe parameter. A could be parameter at the second level, and B could be unit of the parameter, and so on. So C and D, of course, one has to define what the data is about and come up with a semantic description to that. And I think in our example is pretty simple. Parameter is the name of the data. In this case is temperature, rainfall, and temperature has a different unit and rainfall has a different unit, for example. And what else? We could think of also
so
the date.
This schema is really kind of up to you. It's how you would organize your data scientifically. So if this was your holiday photos, you might categorize it by location, date, maybe
Yes.
Maybe what time of year, like summer, winter, obviously you might have the season in there. You could really choose anything here that helps to identify your data.
Yes,
and
exactly.
Obviously, if you're from a different scientific domain than weather forecasting, which I presume the majority of you are, then these rules, you would tune them to whatever your scientific data was. So if you were doing CFD simulations on aircraft, you might categorize them by the type of aircraft, the weather condition, the wind conditions that you are running your simulation in, maybe some other identifiers about what kind of experiment it was, this kind of thing. We have users that are doing things for cryo-electron microscopy, and they categorize things by the experiment number and the type of microscope they were using, and other information about the sample of what they were imaging. So depending on your domain, you may come up with completely different schemas.
Yeah, as James said, that this is up to us what we how we want to define the data semantically, and it's just about finding a meaningful set of keys that we think best describes the data that we have. And in this case, I mean, you could also say username. You could put any key that you think is meaningful and to describe the data. So let me institute. I came up with this, but it doesn't have to. It's just what I came up. Channel. The important thing is please don't put comma at the end here. Let's say we have such a schema, and when you run the cell, it will save the schema file. I can show it. So I saved this file called schema. It's the YAML format and institute channel parameter unit date and time. That's what I came up with. And when you run the cell, this one, then it should save that schema file. So to run it, I'm not sure if everyone is familiar with Jupyter Notebooks. There's on top, there's this play button when you select a cell, such as this one, and you run it. When you click on it, then it's executing what is written there. Thank you. So so let's assume that we came up with this schema rule that identifies or describes our data. And we could have multiple rules in a schema file. So it's not, in this example, we only have one rule, but it could be multiple rules. DASI would handle that automatically. So we need to now archive this data that we have inside this folder called data, which is a list of files, grep files. And these are our original data, our acquisition from simulation output from the weather forecast models. And we create this DASI object pointing to the configuration file for the DASI. And then we need to now create a key. We can already create the key as a dictionary in Python. In this case, institute, ECMWF, channel, global, and in your case, you will define those according to what you came up with. And underneath here, I already implemented this parsing the file names and returning the relevant information about the file names, these metadata that we mentioned. So if you run this cell, then it will create, in my case, this is different. So for you, it should be data. So when you run this cell, then you will see that there is the path to the file, original raw data, and then the name of the data, so rainfall or temperature, and then date, and the last variable is the time. So time is 0, 0, 0, 6, 12, and 18 in this case. We know that this is the range. So we need to think about, okay, here we want to archive data, and we know that we need to make a key for each file. So using the metadata. So in this case, I will use parameter, and I wrote it wrong, parameter. Okay. parameter and then unit. So I think unit is, I will just keep it simple and call it Kelvin, which is not correct for, it is correct for temperature and it's not correct for rainfall, but to keep it simple, I will just call it Kelvin. I could also remove it. So the second one that I need to define is the parameter. So this is the name of the data. And as I mentioned, inside this loop, we already returned the name, which is rainfall or temperature. So, and the second thing I have to define for the key is I came up with date. So I also have this information. And the third one that I need to define is the time. So time, in this case, as such. So I can now print this key and to see if everything is correctly set. So I see that Institute ECMWF channel is global unit Kelvin, parameter is temperature, date is correct, time is 18 in this case, and there's also rainfall. So it seems that the key is correct now. I created this DASI object before, and now I can say archive key, and I need the data. So I need the, I have the path to the original data, so I can say, what I can say is read the file, read file as binary. So I need to open the file, open the with open path and in binary as file, and I can say data file or something like this. You need to, so we need to get some data data in binary so that we can archive what we originally had as a raw data. I'll create the key. So okay, so we need to create a key. We need to then read the data, and in this case binary, in binary mode, and then we archive. So that's the part, that's the actual archival of data that we read together with it is semantic description, and this should then be the DASI archival, and that's it. It is very simple, but it takes some time to understand what the schema is, what the key is, and so on. But if you experiment with it, just do some printing. Okay, what's the key? What's inside the key? What happens? And please also look at the DASI store directory, where when you run the archive, DASI will create those directories and fill up with the data.
So just to note, if you were integrating DASI into your scientific application, it's probably unlikely that you would be reading files just to archive them with data. Probably the data itself would be coming from your simulation directly. So just to clarify, for example, here we're reading file objects and storing them in DASI, but these could very well be the arrays from your application or images or whatever else you were producing that you wanted to store directly from the application itself.
I will talk again what we did quickly, and so we had a original data stored inside this data directory, which was a set of grep files, and each file had a name such as temperature, rainfall, and a date and a time. And we came up with a rule as such: institute channel as first level, and second level parameter and unit, and the third level as date and time. And we could come up with any other description, which just has to be semantically meaningful, scientifically meaningful. And in this case, we already have this function called data, class called data directory. What it does is it would read the directory and return path of the file, name of the file, parsing the name of the file and returning this temperature or rainfall, and date and the time as result. And what we did is we created this key, which is filling up these values in this rule for different different levels of the rule in the schema file. And at the end, then we read the file from this folder and we archive it in DASI store. And if we check the DASI store, then we see that our data is written here. If we run it multiple times, then we will get multiple set of files, because DASI will not overwrite or delete or remove the data saved archived before. So the second task is retrieving the data and plotting this data. And plotting is just something extra. We don't have to, we just want to demonstrate that we are reading the file correctly. So in this case, we want to, similar to keys, we want to create a DASI query object. And using that query object, we want to retrieve the data that we archived before and use it in our workflow. In this case, for example, query is a little bit different than key, as I said, because the values of the individual rules can be more than one value. So we can define multiple values that we want to query from the DASI store. In this case, I have an example as such that time is, I want to retrieve multiple times in 00 or 06. So I want to have both of those data retrieved from the DASI store. In the first, so we have two challenges here. One is to plotting a temperature over 3 days. So we want to retrieve data of temperature and 3 days. So to 11/26, 11/27, and 11/28. And we can say, okay, the time is, in this case, we will use time equals to 0, or we can also say time as multiple, but let's say 0, 0, 0. So we need to come up with a query that would return us the temperature data over those 3 days at time 00. So if you have any questions, please ask, interrupt anytime. Maybe we can have some couple of minutes. Let's wait 5 minutes or 5 to 10 minutes. And in the meantime, please ask if you have a question, if something is not running, if something is not working, or if it is working also. So the challenge is to retrieve the data, and it is here, for example, what could be the query. So I have here, we decided it is institute channel, and also we said we will have unit, but we know that this is always, we said, okay, let's always use Kelvin, so I will put Kelvin here. And so the challenge is to retrieve data, temperature data. So we need to parameter. So we need to define the value of the parameter. In this case, it should be temperature and date. We also, the challenge is to define the date. So we were at this task 1. So in this case, yeah, here. So this cell individually, so is if you run the cell, clicking on here, it would say overwriting schema, which would, at the end, what is important is this file. So this file called schema should be correct. So if here is, let's say, data, and I save it, and then I come back here and try to run this, then it should not work, because here I'm saying that there's date, parameter, and time, and unit called Kelvin. You can call anything else. But when I look at here, it's correct. But when I look at the actual file, which is the schema file here, is different than what I have. So, but if I make a change here, parameter unit, and then run it, then it should overwrite this one, and it should be correct. So important thing is to check this file, please. Schema file, that it's correct. And also maybe I did a change here. I think it was before I did it like this, and I put it here. Please also check that. And there is also, sometimes you need to click on here and shut down all kernels. Sometimes it is distributor thing, breaking things. It could also be the case. So, or the other way is right click on it, clear outputs of all cells, and restart kernel, and then run it again. So for retrieving data, similar to key, we have query, and the queries are a little bit different than the keys, in that the values of each metadata key that we defined in a rule, in a schema file, has to be put in a curly brackets. And the challenge was that, okay, we want to have this temperature data over 3 days, which means, okay, we need to say, I want to query 11:26, 11:27, 11:28. And we said, okay, let's choose time 00. So this would be our query. And after making a query, then we need to retrieve. So if you remember, in demo simple retrieve, I mentioned that you can retrieve multiple data. So what we need to do here is actually this DASI retrieve, this one here, and we need to pass in the query. And then afterwards, we need to check that we retrieved something, and we can look at how many data that we retrieved. So in this case, I will do retrieve, and I will pass the query to that. And I call the temperature because I want to retrieve temperature, and then we can check the length of the temperature object, and if it is less than 1, then we can say print no object or no data found. So, and you can always go to this demo simple retrieve example. You can always look at the example simple retrieve example here. So we need to check that we retrieved something, and we can also print how many objects or data that we retrieved, and then we need to loop over this object that is returned by the retrieve, and in this case also here. So each item, as I mentioned, has key attached in the returned object. So key, we can print this and see item key, and this would be the metadata key. So let's say metadata key, and the other one is the actual data. And there is already plot weather function, so it will plot the function. And let's try. So we retrieved 3 metadata keys. We retrieved 3 temperature data, and we can check now the keys. I'm printing the keys. So the first key is channel global, date is 11:28, institute ECMWF, parameter temperature, time 00, unit Kelvin. That's what I asked for from DASI store, and 26, 27, and 28. Those are the dates. And for each date, we now plot those data that we retrieved, this temperature data. So this is actually very simple, and is the solution for this challenge 1, and pretty much the same thing for the challenge 2 for the rainfall, except that we need to then change this query from parameter temperature to parameter rainfall. And in this case, we also want to rainfall. We want to have a specific date, 11:26, but the time we want to change the time. So we want to have a range of times, so multiple times. So in this case, 0, 0, 0, 06, and 12, and then 18. So we have 4 different times, but the date is 11/26. The date could also be multiple, so at the end we would return multiple dates. And it's the same as the temperature, so we want to pass this query to the DASI retrieve API. So DASI retrieve, and then we pass the query that we create above, and then we already have this plot weather command. And so now what we did was for 2023 11/26 date 600 1800 and 0 and 1200. We have the plots of rainfall for all those times, and that would conclude the retrieve task of the training. And we presented DASI and how we can use DASI to manage your data semantically, describing the data using meaningful keywords and metadata. And you can find more about DASI. The source code is on GitHub. It is open source. It's github.com ECMWF projects/DASI. And we also have C API and Python API examples on the DASI examples. And also we have binary packages on GitHub. And we have documentation as read the docs. So DASI.read-to-docs. We have the source code github.com ECMWF projects/DASI. And inside the source code, you will find examples directory where we have Python API example called histogram and weather example for C API, how to use DASI in a C application. And we also have binary packages on the releases on GitHub, and we have documentation on DASI on read-to-docs at DASI.read-to-docs.io. How to install DASI? We have, as I said, a couple of dependencies for DASI. So if you go to the releases on GitHub, you will see, as on the right, you will see several assets. For building it from source, please, you can use source tarball, and this includes all the dependencies as a source code, and the building is same standard CMake build workflow. And we also have a couple of binary packages for RPM and Debian packages. So for Red Hat and as well as Debian-based Linux operating systems, you can use those. And for the Python API, you can find the Python package called View, PyDASI, and install it with pip. So it is straightforward. So DASI supports multiple backends, and we didn't get into this, but it is also easy to try out DASI on different backends if you have different backends, and what you had to do would be that you just change the DASI config YAML file, where there's store, in this case, is file, which refers to actually to the POSIX backend, but you could use multiple backends. And for DASI, we will in the future add access control feature, and as well as additional backend supports. And that would be the wrap up. And any questions so far?
We had one question in the chat from Edmund about how to read group files. So group files are a World Metrological Organization standard for metrological data. It's what we're using for these examples. ECMWF provides encoding and decoding libraries for this. You can search for EC codes, or more recently the EarthKit library, which is what the plot function here is using underneath. But DASI doesn't have, DASI has no connection to GRIB. We're just choosing to store GRIB here as an example. You can store any binary data inside DASI. So whatever your standard data format is, and I encourage you to find the data standard, whatever that is, if one exists, you can store inside DASI, whether that's PNGs or PDFs or whatever, NumPy arrays, anything you like. Any of those can be stored in DASI and retrieved later.
Thank you very much for really nice training. Well prepared. Thank you all the tutors for the preparation. Thank you very much for attending, and have a nice day.